Next case that we're going to deal with is a convex lens when the object is within the focal length. In this case, the focal length equals 10 centimeters and the distance object equals 4 centimeters. I'm also going to make the height object equal 4 centimeters as well. Okay, so if it's closer, what's going to happen? And this is a typical case that happens with magnifying glass. My eye would be over here, I'd be looking at this and I'd be trying to see what's happening. So again, remember we draw 3 lines. The first line goes parallel and then through F. And F. Remember we've got an F over here and we've got an F over here. So the first line goes parallel, and so it's going to hit here, it's the parallel bit, and then that ray is going to go through F. Cool. So this is going to be ray 1. Ray 2 goes through F, then parallel. So in this case it's a little trickier, like we were doing with the mirrors before. When we do this through F, we put the ruler on F and the tip of the arrow. And then I draw it up. So it goes up from F to there. This should be dashed, I suppose. Let's make that dash line. That just shows it's not a real line. That's a virtual line. Okay? And then it goes parallel. I don't think that's parallel, but we'll live with it. Okay, so this is ray 2. And of course then we have ray 3 through the centre of the lens. Okay, so what we do here, we put it on the tip, we put it on the centre of the lens, and we draw ray 3. So this is 1, this is 2, this is 3. And then we look at that and instantly there's a problem, because these are all diverging. These rays are going to spread apart and they're never going to come back together again. So what do we do in the case of diverging rays? Whenever we have diverging rays, we look at the rays that are diverging and then backtrack them back along their path. Because my eyes are over here, I'll see it coming from here. It's over here, I'll see it coming from here. So what I'll do is grab the ruler, I'll look at the rays that are exiting. Let's just do this one first, no particular reason. And I'm going to backtrack the rays. And remember, I'm backtracking them with a dashed line. I backtrack that ray, I backtrack that ray. And I backtrack ray number 3. Hopefully they all end up at the same place. So we backtrack them all and they all end up here. And so this is literally the case of a magnifying glass, because I look at it and I ask my 3 questions: upright or inverted. So I'm looking from over here, this is my eye over here somewhere, and what I see, this is upright. Then I asked enlarged, reduced, and it's going to be enlarged. This is why it's a magnifying glass. The image on a magnifying glass always looks bigger. And then real or virtual. Can I put a piece of paper here and shine the image on it? And looking at this, in fact, we have to use dashed lines to make the image. It means it's virtual. We cannot physically stick a piece of paper there and shine an image on it. Don't believe me? Go grab a magnifying glass and check for yourself. Okay, so then we've got information we want, DI, DOM. So we can just directly measure these. DI is going to equal, or what's that, 6.5. And it's going to be negative because it's on this side of the lens. Yep. If it's on this, the image is on this side, it's positive. If it's on that side, it's negative. But we'll check that in a second. DI, HI, sorry, I should have said HI. I want to find out how high this thing is. Now it appears, I stick the ruler on it. So about 6.5 as well. And then the magnification, M is equal to HI over HO equals 6.5 over 4. I shouldn't really need that, but so about 6.6. 6.5 divided by 4 equals, what? 1.6. 1.625. So it's a little bit, so it's enlarged a bit. It's enlarged, made bigger. We can also check this out with maths. We can do f prime equals do prime minus plus di prime, and rearranging that like we did the last few times, di prime equals f prime they're not prime, f inverse to do inverse. So di equals f inverse minus do inverse, take the inverse of the lot. So di equals, f is 10. 10 inverse, sorry, f is 10. Do is 4 inverse. Take the inverse of the lot, so go 10 inverse minus 4 inverse equals, take the inverse of that, equals minus 6.67 centimeters. That's minus. So this is going to appear minus 6.7, so that's going to appear on this side of the lens. We said 6.5, pretty cool. HI is going to equal, again from earlier, so HI over HO equals DI over DO, so HI equals HO times DI over DO. What's the height of the object? 4 times distance of the image is negative 6.67 divided by distance of the object, 4, equals, and that's going to equal negative 6.67 centimeters. And what that negative sign tells me is it's going to be upright. And the last thing that we want to do is M is equal HI of HO. So negative 6.67, yep, that's fine, or 6 point. The last thing is we take the height of the image, 6.67, it doesn't matter about the minus sign now. We divide it by the height of the object, 4 equals 6.67 divided by 4 equals 1.667. 1.625. So pretty good, but not perfect.